Another parameter associated with loss of energy is reflection. It's an internal reflection within the cell itself. It's light beam that gets into the cell is being reflected back out. The photons that are being reflected back out do not excite electrons, do not produce current. They are reflected back and out. A cell efficiency can be increased by minimizing amount of light reflected away from the cell surface. For example, untreated silicon reflects more than 30% of the incident light. 30% of the incident light is a lot. It means that if 100% goes in, only 70% have the potential of being converted to electricity. That's why various anti-reflection technologies help us to optimize light absorption. Most commonly, a special coating is applied to the top layer of a cell. A single anti-reflective layer will effectively reduce reflection only at one single wavelength. Better results over a wider range of wavelengths are possible with multiple anti-reflected layers, but that means I have to have a cell of N, P, N, P, N, P with several layers, and each of them will have an anti-reflective layer in between. But I'll get higher energy at the end. Another way to reduce reflection is to texture the top surface of the cell, which causes reflected light to strike a second surface before it can escape, thus increasing the probability of absorption. Let's look at the picture. We see a light beam coming in, it's being reflected to the side, some of which penetrates the cell itself. If the front surface is textured into pyramid shape for anti-reflection, all incident light is bent so that it strikes the polished, but otherwise untreated, back surface of the cell at an angle. This texturing causes light to be reflected back and forth within the cell until it is completely absorbed. It's a very, very interesting technique, now mostly used in major panel manufacturers.